Hello, today we're going to discuss the concept of the derivative. This is going to be a little bit on calculus, and it's going to be very basic conversation of derivatives, and that is that notice here I have a curve that looks suspiciously like y equals x squared, but really it's y equals x to the n. And I take a point on the curve, and I draw a line that is tangential to the curve at that point. We have dy over dx is equal to n times x to the n minus 1. And a lot of you have just kind of learned that and accepted it, and you've moved on to more complicated functions in calculus like a series. And of course you've used it to prove that with a series defining y equals sine x, an infinite series, you can then prove that derivative of sine of x dx would be cosine x. And then you can also use it to prove that the derivative of cosine x dx is equal to negative sine x. But I want to stop with that, and just for those who may be on a more basic level, or those who maybe just kind of accepted that y equals x to that the derivative of y equals x to the n is n times x to the n minus 1. And, you know, it's very mysterious. Why would that be so? It's very beautiful, it's very mysterious, it's very simple. It's one of the mysteries of mathematics from my standpoint. Now, let's put it this way, it's the mystery of mathematics, but it is not a mystery because there is a reason why, but it is mysterious. We'll put it that way. Now, you need to have out in front of you your Pascal's triangle, and let's try to get that. You remember that? 1, and then the bottom there is 1, 1, and then 1, 2, 1, and then 1, 3, 3, 1, and then 1, 4, 6, 4, 1, or just kind of know it by heart. And what you need to understand from your algebra days is that if I have a function like a plus b to the nth power, okay, any n, it's starting with a plus b to the 0, a plus b to the 1, a plus b to the 2, a plus b to the 3. I have a to the n plus, now notice that in each and every single one of those, I have a to the n plus n times a to the n minus 1b plus some series going out to then ending with plus b to the n, okay? In other words, for there we go, a plus b to the 4th, I have a to the 4th plus, okay, and my 4 would be my n. So a to the 4th plus 4, a to the 3rd, b. In other words, a to the n plus n times a to the n minus 1b, all the way out to plus b to the n. Okay, so you're going to have to burn that in your memory because I'm not going to hold this thing up. I'm going to have to return to this. So, keeping that in mind, because that's going to be very important, now I'm going to take a slice of y equals x to the n, and you can see what I'm doing here. Between, let's say, this point and this point would be my delta x, and between this point and this, let's say this entire horizontal line would be my initial y value. And then if I had a horizontal line up here, that would be my y plus delta y. So the difference between the two horizontal lines would be my delta y. So if I then had a slope defined of a line defined by these 2 points, it would be delta y over delta x, right? Just like yeah, you understand. That would be it would be the tangent of this angle, but we're not going to get into trigonometry. It would just be this value delta y over this value delta x, okay? So as I put more and more if I put more and more of these dotted lines until they approach infinity, in other words, an infinite number of these dotted lines, I could move this point, x plus delta x, comma, y plus delta y, closer and closer to xy. And as I do that, the slope of this line approaches the derivative. Okay, so it's very important that I start off with my delta y over delta x is equal to x plus delta x to the n, because again, the function is y equals x to the n, so I would be this point to the n, meaning this, minus x to the n, meaning this. Okay, so this x plus delta x to the n minus x to the n, which is my delta y, over my delta x, whatever my delta x would be. Okay, so notice that the delta x cancels on both sides. So I just have delta y is equal to x plus delta x to the n minus x to the n. Okay. Well, remember your Pascal's triangle that I just showed you? Remember how my first term is going to be x to the n, but then that cancels because I subtracted x to the n here. So what my second term would have been would actually becomes my first term, and that's n times x to the n minus 1 delta x. Okay. Now just take, remember we had a and b, and just substitute in x and delta x. Okay. So go back to your Pascal's triangle, and you should have one in front of you, but I guess I can pull it up again. All right. Be that way. Okay, here we go. So notice how, again, we had, just notice my x to the fourth plus my line where I have, you can see it. There we go. Yeah, you can, hold on. Really professional job here. There we go. X, notice my a plus b to the fourth there is equal to a to the fourth plus 4a to the third b plus something, whatever it is going out to b to the fourth. The bottom line is that the pattern is the same. It's a to the n plus n times a to the n minus 1b plus something going out to b to the n. Okay, so I have the same basic idea here, only I'm using x and delta x, and I'm subtracting x to the n, so my second term is first. N times x to the n minus 1 delta x. Okay, so far so good. Now I'm going to put an infinite number of dotted lines into that curve there, and my delta x can become dx, my delta y is going to become dy, and I'm going to now have dy is equal to n times x to the n minus 1 dx, plus something going out to dx to all together to the n. Now this is not the nth derivative. This is dx to the n. Case in point, never put that on your calculus paper because it opens up too many philosophical problems. How do you have the square of the infinitesimal being something of a different nature than the infinitesimal? Doesn't really make sense when you get into Cantor and the paradoxes around the infinitesimal and infinity. But fortunately, this is going to go away because I divide both sides by dx, and then I have n times x to the n minus 1 plus a bunch of terms with dx, and since dx is infinitesimal, I just don't worry about them. Okay, so that's all covered up. And before it probably would have been better if I had just left this as delta x and then allowed my delta x to go to dx somewhere down here, but it's not really going to present a problem because my dy dx is going to be n times x to the n minus 1, and the rest of these terms are infinitesimal. They don't count. So since they don't count, we're not going to worry about any mathematical paradoxes that are formed around them. So dy over dx is equal to n times x to the n minus 1. Voila. All right. We're now done. We've now affirmed that for every simple exponential curve like this, y equals x to the n, we now have verified this really mysterious fact that the derivative is n times x to the n minus 1. Now, the next one I'm going to do is going to be on integration or antiderivatives, and so I hope that this has been a good and interesting video, and at least fun. Thank you.